So the second talk of this morning is by David Myers, and the topic is logical topology and axiomatic cohesion.
Hi, everybody. So thanks so much for having me here to talk about, this is a little bit of essentially one cohesion. I'm mostly going to be talking about sets today. So I want to thank the organizers if there are plural. If otherwise, I'll thank Felix. So
kind of plural, yeah.
Axiomatic cohesion was, this is one way to tell the story. Levere continuing this dialogue that begins, what is a space? Well, it's an object of a category of spaces, surely. So what is a category of spaces? No. Levere gives a particular, very abstract formulation of what a category of spaces is. He has a sort of Wu-Wei axiomatization. It axiomatizes something by saying what it isn't. So we give three modalities that remove all spatial cohesion in three different ways. So first we have sharp. This is the codiscrete reflection. It removes all cohesion in the trivial sense that the resulting type has just the trivial cohesion between all its points. It's codiscrete. We have flat, whose modal types are discrete. So they have trivial cohesion in that they don't have any cohesion. And so this is the classic two ways that you can negate something in mathematics. You can either remove it or you can trivialize it. And then we also have a third modality, which is shape. So we heard about this yesterday in Mike's talk, and I'll go into it a little more. And this also has modal types being discrete spaces, not necessarily as Mike pointed out. Naturally, we should think of the modal types of shape as sort of homotopy types or homotopical types, and it will be an axiom that these coincide with the discrete types. The action of this is very different from flat. So some gross topuses of interest, so that's big topuses of spaces, are cohesive. And this includes continuous sets, which you'll find in Mike's real cohesion. So these are going to be, and we could do this as, I'm doing this as sets here for a little bit of setup, but we could do infinity groupoids. So these are going to be continuous sets, and that's going to be defined to be sheaves infinity on, we'll have cart spaces, thanks to Mr. Urs. But here, we won't use exactly the same category that Urs did. We're just going to do the category of Rn with maps being just continuous maps. So, in other words, a continuous set is a space which is probable continuously by Rn. And the topology here is the open code topology. And then we also have models of synthetic differential geometry. So Dubois topos and the formal smooth sets that Urs told us about in the last talk. So Dubois topos is, just mention it here because it comes up a little bit later, is going to be sheaves and then, maybe infinity on, well, here we want something that's going to be like what we learned last time, where we take, we use the embedding of Rn with smooth maps into C infinity rings. But here, we're going to take a different kind of way of adding infinitesimals. We're going to take this is going to be the category of C infinity Rn mod I, where I is a certain kind of ideal. And this is what's called a so-called germ determined ideal. And what that means is that a function is an f. So a function is an I if and only if every one of its germs is in the ideal of germs for any x in its domain. So this includes the other category, but it includes more spaces. So for example, in particular, we have in here, we have C infinity R0. So these are the germs at 0 of R, of smooth functions. So this is not in the category that I was just telling us about because it's not finitely presented. And we also have an example from algebraic geometry, which is many topos. And so this is similar to the big Zariski topos, and I think sometimes I will ask you to forget that these are different, which is why I maybe have a too small asterisk there. It's notably different in that it doesn't include a topology, a real topology, but many topos. I'm going to describe it just because it's maybe the one construction I know of that's actually been completed of cohesion in the algebraic setting. So many topos is constructed in this way. So we take here pre-sheaves on finitely presented connected K-algebras. For K a perfect field. And that's just to get away with some temporal extension problems. So these are the connected finite affine schemes, basically. This is the idea. And then we take down here, we're going to take just finite extensions. Okay. And those sort of, well, this category includes into there, and it has this category includes into there in the obvious way, and it has an adjoint, which is non-trivial, which essentially takes a connected K-algebra to its field of definition. So this fails rather drastically if the K-algebra is not connected, because, for example, take a product of two fields. Now you don't know which one it's really defined over. Turns out if it's connected, then a quick argument shows that you have an adjoint. And so you get an adjoint quadruple in the way that Erzschiff said, which looks a lot like, which looks a lot like cohesion here, except it isn't. And that's because this fails to preserve products. However, if we take sheaves on this for the atomic topology, and that's the topology which is generated by single elements, so in other words, every map is a covering, then we can pull back like this, like topos is, and this is many topos, and this map here exhibits cohesion. So as a particular example, if your field is algebraically closed, then this thing is set, because this thing, finite extensions of an algebraically closed field, is a point.
Sorry, what is the lower left corner?
That's sheaves on finite extensions with the atomic topology.
I see.
So this is also equivalent to continuous actions of the profinite Galois group of K. So in particular, because this is continuous actions of the Galois group, if you have a C vector space in here, that's a Galois representation. And that's considered to be a discrete object in the resulting cohesion. Okay, so in all of these models, there are suitably nice spaces that we're used to. So in particular, in the first two, we have manifolds, either continuous manifolds or smooth manifolds. In the third, we have suitable schemes. And I'll say suitable schemes to avoid particularly saying what actually went in the site. So if I use a bigger site, my suitable schemes becomes more. But as it stands, I need something like finite type separated schemes. And they all have topologies on their undersigned sets. And we know what we mean when we say the topology on a manifold. We mean say, well, a manifold axiomatically is a topological space equipped with some extra structure or some extra properties, and a scheme as well. Now, in his thesis, Jacques Myers defined a logical topology, which is held by any type. So he did this in one topos theory, but we can just write it down in type theory. And this is the definition. And don't look at it too hard, because I'm actually not going to use it for the rest of this talk. So you don't have to remember this, but I figured if I said he defined a topology and didn't tell you what it meant to be open, you don't get mad at me. So here it is. So this has a nice little picture. So if you have a space here, and then you have some kind of open in it, don't make my space a little fatter. You have some kind of thing you declare to be open in it, right? What it means to be non-open is that if I take any point in here, and then I take the whole space punctured at that point, then these two maps here, these two subspaces here, together cover. So in particular, the axiom that the general multiplicative group is non-open in the affine line in the topos of the ring classifier topos, which is pre-sheaves on finitely presented K-algebras, is equivalent to asking for the Zariski topology to hold there. So this is somehow a notion that's related to Zariski open. And in particular, Canal and Dubuc together proved that in the 3 examples I mentioned, that logical open is the same thing as regular open for logically separated spaces. So
ordinary open?
Yes.
Regular open also has another meaning.
Right. Usual open. So I actually had the word usual here, and then I changed it to specifically what I meant, because I foresaw that happening, but I said it anyway. So in continuous manifolds, this means like the epsilon ball open, and by that I mean, like, you know, so you might not have that on the general manifold, but if you have a manifold embedded into Rn, it means that. And for separable schemes, it means the Zariski opens. So the question I wanted to ask is, how does the logical topology on a type compare with its cohesion? All these examples are cohesive toposes, asterisk, but and they have this logical topology, we might naturally ask. So, for example, in his real cohesive paper, Mike showed that every crisp function from R to R is epsilon delta continuous. So we might naturally ask, what is the topology of R? Now, that's a great question. Unfortunately, I'm not going to answer that today. I'm just going to give you 2 glimpses of this, which are really 2 questions that I just wanted to know if they were true, and they are. We're going to see if the path-connected components, which are defined via the cohesive modality, are the same as the logical connected components of a type. And we're going to see that a set is Leibnizian, which is defined through cohesion. It's one of Lever's definitions he gave in his original axiomatic cohesion paper, if and only if it's De Morgan, which is a logical notion. And those are a lot of words, and I will define all of them in the coming talk. So, just see how much time I have. All right. Okay, so in his real cohesive paper, Mike gave a cohesive type theory, which he talked about yesterday, and I'm just going to do a brief refresher of this. It's helpful. So cohesive type theory differs from your vanilla homotopy type theory in that it has 2 kinds of variables, one which are for emphasis called cohesive variables, and the other which are called crisp variables. Now the idea is that if we don't assume any classical axioms, it turns out that types have a lot of sort of topology hiding around. Now there might be many reasons for this topology. One of these reasons is that there are models of intuitionistic type theory in settings of where the spaces have continuity. And therefore, all functions there are continuous. And so, in a sense, any function you can define in the type theory must be continuous. But there's also a sense coming from computability. And we're here not going to be doing the computability part. We're going to be thinking about these things as coming from the spaciness of our types. And so we can add a new kind of variable. And this variable will be a crisp variable. And we think of this as being a discontinuous variable. So I like to think of this as giving us the difference between the universal quantifier for all and the universal quantifier for each. So a crisp variable is something that holds for each variable, maybe independently, maybe separately. But when you say for all, that's somehow generic. And we can formalize that. We can say, following Mike, that if we have a crisp proposition, that's either true or it's false. And in other words, if we have something crisp that we're trying to do, we can argue by cases. So we can have each of our cases one at a time. So intuitively, this says every discontinuous proposition is either true or it's false. And we're also going to assume something else about our spaces. We're going to assume that locally, they are probable by some basic contractible spaces. And I'm going to do the same thing that Mike did in this talk, when I'm just going to say, instead we're just going to do it, assume it's just one space, which we think of as an affine line. In the settings, it will be either the real numbers, by which I mean the smooth real numbers that second time, or it will be question mark, because it's probably not just the affine line. In fact, it definitely isn't. So we'll talk about that after the talk. So this is our axiom, which we call punctual local contractibility. And this is local contractibility we learned about yesterday with a further requirement. So local contractibility says that X is discrete, and remind you, discrete means we have the reflection flat X, which we can think of as the crisp points of X. We have X as a type, and this is crisply discrete if this is an equivalent. So that is another words of saying it's modal for flat, except that this is a comonadic modality. So it's not literally the same notion, but it's basically the same. So we fixed that the crisp types are discrete if and only if every path in them is constant. And we also asked that there's actually a point 0, so in a sense we can evaluate these paths at something. This is certainly satisfied in the real models. No. So we can consider a map from A to X to be a path in X, and this means that the shape, which is the localization at A, the nullification at A, should be the homotopy type of a given type. In other words, it takes any path and it turns that into an equality in a way that remembers exactly how those paths were put together, reflected in the equalities. We might call it the fundamental infinity groupoid, but this is entirely in type theory, so I might just use the word type again. And we'll consider this as a discrete type, so this ends up being discrete. And therefore, we could define the set of path components to be the zero truncation of shape. And this is also a modality I might note. Its unit is going to be the composite of the two units of these two modalities. And its universal property, mapping property out, shape not, or esh not, is going to be essentially the join of the two mapping properties in the sense of it will have, shape has a mapping property into discrete types, shape not will have a mapping property into discrete sets. So, if this is the path components, are they the connected components? It's a natural question. The answer is yes. See that now? We'll need a few definitions. So this is some elementary power set stuff. So the power set of a type is just the maps from A to prop. This is a set because prop is a set. And the order on subtypes is given in the natural way, as P is contained in Q if everything in D is in Q. And we can also define the usual subtypes by pointwise optimization. So the intersection is the pointwise and, the union is the pointwise or, the complement is the pointwise negation. Oh, we'll say a subtype is merely inhabited if there is merely an A that satisfies it. So if there's merely something in it. So by merely, just in case, so by there is merely an A of type A, I mean we have some A, maybe class of A, of type the -1 truncation of A. So in other words, we have one, but it's not part of the structure. And a subtype is detachable if for all A, either it's in the subtype or it's not in the subtype. This condition does a lot of work. So I will leave that up here. I'm going to go ahead and erase everything I just wrote. So if we have some space here, that's not going to do. Spaces might have multiple components. They're not just potatoes. They might be sacks of potatoes. And so to say something's detachable means that if I say a part of it, right up here, then the negation of it, the complement of it, is the largest subspace which is disjoint from it. So for A to have a detachable subspace, it must be a disjoint union. So here is U. Here then is not U. There's the whole space. But you certainly can't have this happen if U was just this part. Because then not U would be that part, which is a disjoint union. So if this is connected, you can't have that. And finally, we'll say a subtype is logically connected if whenever it is contained in a disjoint union, it is entirely in one part. So this is a positive way of saying, in the sense that something is logically connected if it's not disconnected. If something was disconnected, right? So, for example, this chunk here should be connected. So this is contained in, we might say if this was contained in this disjoint union, it would have to be wholly in one part. But it's not, because we're actually missing this little bit. This is a failure of law of excluded middle here. This is precisely the excluded middle. However, it is contained in the disjoint union of these two parts, because it's wholly in here. And so we can define a logical connected component to be a subtype satisfying these three properties. So it's inhabited, it's detachable, and it's logically connected. And as a nice little lemma, we note that if you have two logically connected components and their intersection is non-empty, then they are in fact equal, which is rather strong. That's non-empty, it's not inhabited. So. Okay, so let S naught be the set truncation of S, the set of path components. And we would think of the elements of S naught as being a path component. How do we think of that? Well, we have this map sigma naught, which is the unit of this modality, and we interpret that as sending a point in A to its path component. And therefore, the inverse image of any U in S naught of A should be the actual path component. So for example, if this is A, this here, these 2 points, now I'm going to get A. This should be S naught of A. It's not S of A because I had to maybe some topology here, but I kill that. Right? And with the map, sigma naught just sends this to there, and this to there. So if this is U, sigma naught star of U is this chunk. And so we would hope that this would be a connected component. And indeed it is. We can prove it. So it's merely inhabited because sigma naught is merely surjective. And so this is due to Mike in his paper that if you have pointed local contractibility, then the shape unit is merely surjective. And shape naught of A is a discrete set, so it has decidable equality. Now, this is also, well, this can be seen because it's a set, so its equalities are propositions, but it's discrete. So, well, let's say this. This is due to a lemma by Mike, so.
It's an axiom,
right? Right, yeah. It follows from the crisp law of excluded middle. But, yeah. And then so finally, we just have to show that it's logically connected, and this is where we do something minorly interesting, is we are going to take our connected component, and we're going to put it in a disjoint union. So now what we can do is we can take the actual connected component itself, this is this subtype here, and we can map it into the Booleans. And we'll send it into 0 if it's contained in the left half of the disjoint union, and to 1 if it's in the right half of the disjoint union. But if you look at this subtype, you'll notice it's just a fiber. Right? So as we learned from Egbert on Monday, yesterday, these fibers are modally connected of a modality. And so in particular, this is modally connected. And the universal property, oh, and I'll say that, so in other words, if we take this fiber up here, if this is U, this is sigma naught star U, and this is shape not connected, it gets mapped to this, which is just a point. It says, therefore it has to map either into 0 or 1. And by construction of the map, which is we argued on cases, we therefore have that it's either entirely in one half of the disjoint union or the other. And this map is an equivalence. So for any logically connected component, you can push it forward down into shape not, and that will give you a path component. So as you might expect, local contractibility means that path connectedness is basically the same thing, roughly, as connectedness. So now I'm going to switch gears a little. I'm going to do a little bit of infinitesimal stuff. So this is also Fanon. This is part of Fanon's thesis. Fanon's thesis is called From the Infinitesimal to the Local. So this is the infinitesimal part. Kind of started with the local part. And this is a short monograph paper. I'm doing some claims about this. So the one claim, citing Koch, is that in the big Zariski topos, or Tal topos, with A being the affine line, if you take the set of all points in the affine line internally, which are not equal to 0, what you get is the set internally of the nilpotents, which is the spectrum of the formal power series ring. So I have a picture for that too. We have a line here. And then here is 0. So here is not 0. And so what happens when we do non-0? Well, classically we'd go back to just 0, but of course non-0 is sort of this little open interval in here. This is not 0. So if we take Earth's magic magnifying glass, we'll find in there all the infinitesimals that we might have put into the site. Fanon himself proved, I believe, in his thesis, that in Hooke's topos, with A being the smooth real line, the sheaf co-represented by C infinity R, this same process gives us the actual whole sort of the sheaf co-represented by the germs at 0. So this is, in other words, this set of germs, not of any particular function, but of in potential. And so this leads Fanon to make the following observation or claim. Therefore, we are justified in writing not 0 equals the set of infinitesimals. Question? Yes.
What was the simple one previously?
This is a yo, the Japanese character for yo, for Yonida. Nice. Okay. So we can, the thing I learned from Emily. Okay. So if you type and have two elements of it, we can say that A and B are neighbors if they aren't distinct, if they are not equal. This is, of course, a proposition. It's very weak for types with topology, but it's actually quite interesting for sets. I'm sorry, for types with homotopy, higher homotopy. Right? So this is 2 points being not equal is strictly weaker than them being merely equal. So for example, a connected type has a property that all of its points are neighbors, but that doesn't tell you much because the interesting stuff is happening on the inequalities, right? So I'm going to work with this, and this is a reflexive, symmetric, intransitive relation. It's an equivalence relation. And it is preserved by any function. So this is saying somehow that all functions are smooth. So if we define the neighborhood to be the type of all neighbors, then we can define the germ to simply be the restriction of our function. And this does give you the right germ if you do it in the right topos. That blank there is just the proof. And we have the chain rule. And I like this a lot because I'm TAing multivariable calculus right now. And this is the same chain rule. And in fact, how do you prove this? It is just dependent composition. So the thing that always confuses my students, which is namely derivative of the outer evaluated at the inner times the derivative of the inner, that's how you compose dependent functions. So it's a little nice dependent type theory all the way down. It's fun. And now I'll refresh you a little bit more on cohesion. So thanks to Mike, we know that sharp is left exact. So that means this equivalence holds. It's one of the ways of saying it. And we also know, thanks to the law of excluded middle, which should have been mentioned, that for any proposition, its codiscrete reflection is just its double negation. This is really kind of cool. We know from thinking about negation as subtypes that negation has to do with disconnection and double negation. Here, to prove a double negated property or to prove a negated property, you can actually use sort of classical logic by the double negation translation. This is a fun little exercise, right? Because you know, if you're not A implies B, not A implies not B is the same as A implies not B, right? So you can actually use a little bit of constructive logic in there. And this says, yeah, if you assume that your crispness is discrete in that sense, then these are the same senses of discrete. And in fact, if your crispness has stronger properties like axiom of choice, now you can use that to prove negated propositions. Cool. So putting this together, we find that for any set, two elements are neighbors if they are by definition not equal, which as we just saw is being sharp equal, which is the same thing as being equalized by the unit of sharp. And I put the if and only if symbol there to remind you that this is really because A equals B is a proposition. This is something that happens in this sort of trivial setting, and it's not something that happens sort of in general necessarily. So as a corollary, we find that 0 is the only crisp infinitesimal. In other words, one way of saying this is if you write down a number which is not 0 in the empty context, that number is 0. Right? This is a way of exploring what normally I think confuses people about synthetic differential geometry is you have sort of quote-unquote enough infinitesimals, and yet you don't have any particular ones other than 0. In fact, in particular, you only have 0. And infinitesimals are necessarily variable quantities. They are quantities in flux, which is what Newton thought. Kind of cool. And in fact, since we have by this that the neighborhood is just the fiber over x upper sharp, we have that all formal disks are sharp connected and they're infinitesimal in this sense. And so in particular, if everything there is crisp, that's equivalent to saying this. Or by this I mean a singleton that just contains, say, the center of the disk. So it's the general. And with this, you can do a lot of the stuff that Felix does in his thesis. If you take your left exact modality not to be I, but to be sharp, at least with sets, things start to look kind of similar, which is kind of interesting because a lot of interesting spaces are sets. All right, so Levier gives a definition, and this definition is called Leibnizian. It's supposed to capture the intuition of what it means to have a cloud of Leibnizian monads. That's not monad in the sense of category theory, that's monad in the sense, really, we'll say, of infinitesimal disk. This is the naming convention. So we can say that a set is Leibnizian if the sharp functor applied to the shape unit is an equivalence. So if these things are crisp, this is the same thing as, by effectively transposing in the adjunction, the points to pieces transform, as Ruiz calls it, being an equivalence. In other words, every piece, every path-connected component has exactly one point. And so, in particular, we can think of every chunk of this having a single focal point, a single fixed focal point. It should really look like a disjoint union, discrete union, over a set of infinitesimal points. And for a set, we can take its Leibniz core, which is Leibniz in this sense. I actually have no idea what this does for a general space. I'd like to know. So I might just make a note that if you stick a non-set in here, like say BGLN, what you get is the moduli stack, I guess, of pairs of vector bundles, one of which has a flat connection, which agree on every point. What does that mean? I'm not sure. So that's why I said restrict this to sets. Then this is just going to be a disjoint union of the formal disks. And so a set is Leibnizian if it is equivalent to its Leibniz core. And a set is De Morgan if the neighborhood relation is decidable. So in other words, either 2 points are neighbors or they are separate. So although the not neighbor relation is a triple negation, it's the same as not equality, but I wanted to emphasize that we're deciding the neighbor property. So we can prove that a set is Leibnizian if and only if it's De Morgan.
Where's the word De Morgan come from?
This is equivalent to asking for the De Morgan laws in the in the power set, but not full classical logic. So if you double negate everything in the De Morgan laws, they're both true in constructive logic, and so this says effectively that everything's double negated. So we can compare this theorem here to the theorem that might prove that says a set is discrete if it's decidable. So here we take equality, either things are equal or they're not equal, that's the same as discrete. If we weaken that to neighboring, then that's the same as De Morgan for sets. And so I'm going to end by showing you how to do this. So if it's Leibnizian, and remember that will mean that, well, I'll write it like this. So that's not formally valid for everything because to form flat, we needed it to be crisp, but that's the easiest way to think about it. So if it's Leibnizian, then we also have that shape of sigma naught as an equivalence. So the axiom was that shape of sigma, sharp of sigma was an equivalence, and now we have sharp of sigma naught as an equivalence. And so for any A and B, we have either sigma naught of A equals sigma naught of B or not, because the shape naught, the set of path components, is a discrete set. And so pushing forward with a little typo, we find that the inclusion into sharp shape naught is either equal or not, and naturality lets us move this around. But by hypothesis, this was an equivalence, so we can take off the sharp sigma naughts, and there we have either A is equalized, A and B are equalized by the unit of sharp or not, which was again saying that they're neighbors or not. Now, on the other hand, if it's De Morgan, then we can give an inverse. And what we do is we take any, so any point U in the codiscrete reflection of the shape of A, and we send it to X sharp, where sigma X is U lower sharp. Now, why can we do this? This is a lot of things that seem to involve choices and constructions. The lower sharp is something you can only do. Unfortunately, I didn't go over this. I didn't go over this.
I will.
Lower sharp is only something you can do when U is crisp. U is not crisp. But we're mapping into a codiscrete type. So in other words, we're mapping into something go discrete, we could effectively assume that we were discrete. In other words, we can assume our variables are crisp. And so we assume U is crisp, so we can lower sharp it, and we know that sigma is merely surjective, so there is such an x, and then we send it to x upper sharp. And this only works now if this is constant, because we're mapping into a set. This is, I believe, I don't know who this one is, 2. I usually cite Krauss. But, so this is well defined, since for any y in the fiber of sigma x, in other words, any other choice we could have made for x, we can send it to 0, 1 according to whether or not they're neighbors, right? We assumed that that was decidable. But now we know that this map, again, is going to be, that fiber is going to be shape connected, therefore mapping into a discrete type. It's got to be constant. So either they're all neighbors or they're not all neighbors, and x is a neighbor to itself. So all of them are neighbors to x. And therefore, this is a little infinitesimal disk. And so they are all equalized by the unit of sharp. And that, no, then you check that that's an equivalence, but that proves that. So that's all I got.
Okay, thank you, David. We have some time for questions, so don't hesitate.
So at the beginning of the talk, you showed that logical topology thing. Is that immediate for all spaces in classical logic?
In classical logic, every set is open, and in fact, every set being open is equivalent to being decidable. So in particular here, being non-discrete is the same as being cohesion discrete. And the natural question, of course, is whether being non-codiscrete is the same as being codiscrete, and I have no idea. But in classical theory, the entire thing degenerates.
Okay, yeah, I was confused. I was like,
every function is continuous with regards to the Pinon open, so Pinon topology. So it can't say something special about sets. Yeah.
Do you have any thoughts or anything to say about the Pinon topology, characterizing it more? Like,
yeah, if you assume that being a real number being bigger than 0 is codiscrete, I believe you can show from that the Pinon topology is that every epsilon open in R is Pinon open. I don't know if you can go the other way. So of course for in the sort of Zariski setting, this doesn't quite literally apply, but the Pinon openness of various things is actually just built into the axiom that A is local. So you don't have any choice there, and you can't prove it without assuming that either. So.
One question? Yes, Mike again.
right, so I've thought about this Pinon topology, and I've tried to do things like this, so I'm happy to see that you've made some progress here. But the Pinon topology is a little bit funny from a point of view of a Brouwer-Bishop constructivist, because it uses the disequality rather than some notion of apartness, which is sort of a more sensible thing to put into a definition like that. It's when people who study constructive algebra and so on talk about anti-subgroups and whatever, and open subset, they generally satisfy this Pinon open property, but with apartness rather than disequality. So obviously not every type has an apartness, but I wonder, I don't suppose you've thought at all about whether there's some notion of type with apartness that might make these sorts of things easier to prove, or I don't know.
I haven't, but I have thought a little bit about why apartness doesn't appear as much in cohesion.
Well, one reason is that axiom you mentioned, right?
Right.
Principle in that case.
The motivation for this axiom is sort of that as we add stronger and stronger axioms onto our discretes, namely logical axioms that are highly non-constructive, we're removing more and more of their computable topology. And in the sort of, limit of this process, as we've had to say, why not? We assume the generalized continuum hypothesis for discrete sets, right? So that everything is extremely rigid down there. Then there's absolutely nothing constructive going on, and so the models will then justify the assumption of other axioms that lift that up into the cohesive world, namely, for example, that testing for disequality on the real numbers is in a parsetness relation to normalism, simply because we're saying that we don't care how you check, just whether it is or isn't at each point. I don't know if that, but the answer is no. So, for example, in the Zariski case, it's also you don't need an extra apartness that not equal suffices as an apartness.
Oops. Maybe more a remark than a question, but it ends with a question mark. So it seems that really, or one very important consequence is what Felix has been talking about recently, is that once you say, okay, we have a means of identifying the infinitesimal disks from pure topos theoretical constructions, pure logic, then there's a chance to maybe construct more the system of modalities without assuming anything about size, just by proceeding internally.
Yeah. So
the idea is, if once you've isolated the form with the universal formula disk or something, well, yeah, I guess you've talked about this, and then the maps from that to itself, the space of maps should actually be a smooth space, right? Like the Cochlear axiom say, if you take the first one-dimensional disk, the maps to itself should be actually R times R, R2, with a smooth structure. So I don't know. So that's a remark. I don't know. Somebody should think about how far we can push this now.
Yeah, I would really like to know how to go up, because the deficiency in thinking about sharp as a modality which kills infinitesimals is that it does a lot more. So, for example, sharp bool is not bool. Bool, being a two-element set, has no infinitesimal, so something much more is happening.
That's exactly the point I'm getting. So sharp, if you remember this diagram, it's down at the bottom here. There should be this way to climb up these stairs to get in, which is the finer
right
kind of witness of the infinitesimality. But of course, at least in the model, this im is built from just the disks. You put the disks in a side and then you check the infinitesimal.
Yeah, so I don't know what happens if you just contract the infinitesimal disks of the so basic contractible spaces. I don't know if you get in. But I suppose if you could force it to be left exact, then you could get something that would work like that. I mean, it would refine by definition, it would refine shape.
Yeah, something like this should be tried.
Yeah, definitely.
Felix, your question?
Yep. So related question: can you describe in any way what the type of propositions, the object of propositions, looks like in many topos? So do you know?
Other than it being
how it looks, basically.
No, is the answer. So I don't actually know the topology on the site of many topos because it's determined by it being a pullback of toposes.
Yeah. Okay.
But even ignoring that, if you work in the pre-sheaves, as far as them, I know them being C. So I don't know, for example, what type of not true propositions is. I know that, for example, in very basic combinatorial models of cohesion, you can recover the line object there. So, for example, in reflexive graphs, if you take all the propositions with are not true, that turns out to be a graph with a single loop. If you look at its pointed endomorphisms, you find that a retract of that is the single edge, and so you can recover as a retract of this blob around truth the basic contractible space you started with. I have no idea how far that extends, but I really like it.
It's probably pretty hard to calculate in any more complicated model.
Well, it's hard for me.
Okay, well, I think we can thank David again.
here again at 2.
I got an answer about the